pressure will vary with elevations. As you go deeper from the water surface, the pressure will become higher. So you would like to find the equations that will allow us to calculate how the pressure varies with elevation. So let's say we have a fluid. So this is datum, the bottom part. And then this is the fluid surface. I would like to know how the pressures varies within the fluid. So let's consider an element of fluid. So in this case, let's say we consider cylindrical element. And let's say the length of this element is equal to delta L. And the area here is equal to area delta A. So this is delta A, this is also delta A. And this is the axis. And let's call that direction is L directions. So the force which is acting here is equal to P delta A. And the force which is acting here will be P plus delta P delta A. And let's say this angle is equal to alpha. Another force is the weight. And let's resolve that to the component. So this is the weight. So the weight is equal to the density multiplied by the volume. Volume is delta A delta L multiplied by the gravitational force. We can also observe that if this is delta L, and let's see the height here, that is delta Z. So this is the Z axis, so this is the delta L axis. So we can write that sine alpha, so this is alpha, is equal to dz over dl. Now let us balance the forces in the directions of L. Balancing forces in L directions. So we have the force here, P delta A, must be equal to the pressure force this way. So P plus delta P delta A plus the components of the weight in this direction. This is also equal to alpha. So plus rho delta A delta L T sine alpha. But we know that sine alpha is equal to dz by dl. We can write, since this will kind of like cancel with this, so we can write delta P delta A is equal to, bring this to this side, minus rho delta A delta L G, and sine alpha is delta Z over delta L. Delta A will cancel, delta L will also cancel, so we can write delta P over delta Z is equal to minus rho G. So in a limit as delta Z tend to 0 of delta P over delta Z, so this would actually become dP by dz, and that's equal to minus rho G. So generally, this equation says that the rate of change of pressure with Z is actually equal to minus rho G. So since Z is positive this way, that means that as you go deeper, the pressure will increase at the rate equal to rho G. So for incompressible fluid means that it is not compressible. So rho is actually equal to constant. So this means that you can write dP by dz equal to minus rho G. So if we integrate dP, we can take both rho and G outside the integral. So we can easily integrate this. We get P is equal to minus rho Gz plus a constant. If you rearrange this, so we have P plus rho Gz is equal to constant. There is a name for this. This is called isometric pressure. If we divide everything by rho G, so we have P over rho G plus Z is equal to this constants divided by rho G. So it is another constant. This is called isometric. Okay. So we can conclude that in any static fluid, isometric pressure, which is P plus rho Gz, is constant anywhere within the fluid. Based on the equations that we derived earlier, let us consider pressure variation within two composite fluids. So we have obtained earlier that dP by dz is equal to minus rho G. So if we have two fluids, let's say this is fluid A, where the density is rho A, and this is fluid B, where the density is equal to rho B. And let's say rho A is bigger than rho B. If I were to draw the graph of this is pressure, this is Z, draw the gauge pressure variations in fluid A, which is bigger than fluid B. Say this is how pressure varies with Z. So this gradient will be equal to minus rho A G. So what about for fluid B? Fluid B, the density is lesser than fluid A. So the gradient will be lesser. So if we draw the pressure variation with Z, it will be like that. Whereby this gradient is minus rho B G. If we put these two fluids in one container, this is what we will get. Since density of B is lesser than density of A, fluid B will settle on top of fluid A. Right. And then if I were to draw how the gauge pressure varies with Z, what I will get is that, first of all, for fluid B, the gauge pressure is 0 there, then it varies like that. Then after that, within fluid A, which has higher density than fluid B, the gradient will be larger. So it will be like that. And then at this interface here, we can only have one value of pressure. And that's why it has to be continuous. So this will be the pressure variations. If I just extend that a little bit by considering three fluids, let's say this is fluid A, and this is fluid B, and this is fluid C. And if I were to draw variations of pressure against Z, what I will get is, of course, the gauge pressure is 0 there, then smaller gradient there, and then a bigger gradient there, and then a even bigger gradient there. That would be the pressure variations. So considering this diagram here, so which one of these pressure distributions diagrams is correct? A cannot be true because you have two values of pressure at the interface here. C cannot be true because dP dz is bigger in fluid B. And D cannot be true because the density of the fluids are different. Therefore, the rate of pressure change with elevations will be different. So the correct answer will be B. We have concluded earlier that in any incompressible fluid, the piezometric pressure and the piezometric head in any static fluid is constant throughout the fluid. So if we consider static fluid in a container, that's the water surface. So we can define our datum, that is datum where our Z is equal to 0, and let's call that 1.1, where the pressure there is P1, and call this 1.2, where the pressure there is P2, and call this 1.3, where the pressure there is P3. So then this will be my Z1, this is my Z2, and this is my Z3. So I can write an equation which says that P1 plus rho G Z1, where rho is the density of the fluid, must be equal to P2 plus rho G Z2, and must be equal also to P3 plus rho G Z3. And that summation is called piezometric pressure. Right. So we have P plus rho G Z is equal to piezometric pressure. It is constant anywhere within the fluid. P is what we call static pressure. Rho Gz is pressure due to elevations, due to height, and that must be equal to piezometric pressure. If we divide everything by rho G, what we will get is P over rho G plus Z must be equal to piezometric head. You notice that the dimensions now of all of this is actually length, and the unit is meter, right? So P over rho G is called static head, Z is called elevation head, and this is called piezometric 8. Okay. So using the isometric pressure equation, we can obtain the pressure at a point H below the water surface. So let's consider a point H below any fluid surface. So let's say this is a point A, whereby the distance from the water surface is H. And I can call the water surface as point P, right? So we can draw our datum, which can be anywhere. That is where Z is equal to 0. So this will be ZA, and this will be ZB, right? So if I apply the piezometric equations from, let's say, from B to A, so I can write PB plus rho GZB must be equal to PA plus rho GZA. So I get the value of PA is equal to PB plus rho G ZB minus ZA, right? But ZB minus ZA is equal to H, right? And then PB is actually equal to PATM. So I can obtain PA is equal to PATM plus rho GH, or PA gauge, which is equal to PA minus PATM, is equal to rho GH. So now we can see that the pressure at a point H below the water surface is equal to PATM plus rho GH, or the gauge pressure is equal to rho GH. So now if I extend this a little bit to consider pressure difference between 2 points, let's say this is point A and this is point B, where the height difference between the 2 points is H. So I can draw my datum again, where Z is equal to 0, and that will be my ZA, and this will be my ZB. So I can write the equation which says that PA plus rho GZA must be equal to PB plus rho GZB. So I can write PB is equal to PA plus rho GZA minus ZB. And I know that ZA minus ZB is equal to H. So I can write PB is equal to PA plus rho GH. Right. So basically, we can see that the pressure at point B is equal to pressure at point A plus rho GH, where H is the height difference between A and B. Now, what if we have two fluids on top of each other? So we have two fluids. Let's say this is oil and this is water. And the density of oil is rho oil and density of water is rho water. So now we do the same analysis. So let's say this is our datum again, where Z is equal to 0. And I define 3 points, point 1 here, point 2 here, point 3 here. Let's say we ask to find expressions for P3, pressure at the bottom here. So we define our Z2 is here, and Z1 is here, and of course Z3 in this case is 0. So if I apply isometric equation from 1 to 2, I have P1 plus rho oil G Z1 must be equal to P2 plus rho oil G Z2. That is my equation 1. Then I apply from 2 to 3. So I have P2, but now I have to use raw water, must be equal to P3 plus raw water G Z3, equation 2. From equation 2, I have P3, which we want to find out, is equal to P2 plus raw water G Z2 minus Z3. But from equation 1, I have P2, which is equal to P1 plus rho oil G Z1 minus Z2. And let's say this is equal to H1 and this is equal to H2. So Z2 minus Z3 is equal to H2 and Z1 minus Z2 is equal to H1. So I can write P3 is equal to P1 plus rho water G H2 plus rho oil G H1. Right. So basically, what we have here is that P3 is equal to P1 plus rho oil G H1, the elevation difference here, plus rho water G H2, the elevation difference here. Okay, please take note that we can only apply the isometric equation within the same fluid. So meaning that here we can apply from 1 to 2 and then from 2 to 3. We cannot apply the equation from 1 to 3 directly. So means that we cannot write P1 plus rho oil G Z1 is equal to P3 plus rho water G Z3. This is wrong. So now if I generalize, and let's say we have 4 fluids on top of each other. So this is the surface, and let's say the density of this is rho A, rho B, rho C, and rho D. Then let's say this is the datum where Z is equal to 0. Then if I define here 0.1, 0.2, 0.3, 0.4, and let's say the height here is H1, H2, H3, H4. So by this, I can define this is my Z4, and this is 0.5, yeah? And this is my Z3, this is my Z2, and this is my Z1, right? So I can easily write equation for P5. P5 will be equal to P1, which is PATM, plus rho A G Z1 minus Z2, which is H1. That will give me the pressure here, and plus rho B G Z2 minus Z3, which is H2. That give me the pressure here, plus rho C G H3. The H3 is Z3 minus Z4. This gives me the pressure here. And the last one is plus rho D G Z4 minus Z5 is H4. So I can write this straight away. So now let's say we have a manometer systems which is being used to measure pressure inside a pipe. So let's say we have a pipe here. So viewing from the cross sections of the pipe, and then this is connected to a manometer system that looks like this. And let's say we are using 3 fluids. So this is the first manometer fluid, and that's the elevations. And let's say the density of this fluid is rho A. Then let's say we have a second fluid here, where the density is rho B. Let's say we have a third fluid here, where the density is equal to rho C. And then this fluid itself has a density of rho D. Let's say this height difference between these two is equal to H1, and then between these two is equal to H2, then between this and this is H3, then between this and this is H4. And let me define this as 0.1, 0.2, 0.3, 0.4, and 0.5. Right? So we asked to find P5. Right? So if I define my datum, then datum can be anywhere. That's my datum where z is equal to 0. So this will be my Z1, and this will be my Z2, this is my Z3, this is my Z4, and this is my Z5. So by using the equations that we obtained earlier, I can straight away write the expressions for pressure here, starting from this pressure here. So I can write P5 will be equal to P1 plus rho A G Z1 minus Z2 plus rho B G Z2 minus Z3 plus rho C G Z3 minus Z4 plus rho D G Z4 minus Z5. Right? And we know that P1 is equal to PATM. Z1 minus Z2, Z1 minus Z2 is H1. And then Z2 minus Z3, Z2 minus Z3 is minus H2. Then Z3 minus Z4, Z3 is bigger than Z4, so this is H3. And Z4 minus Z5, Z4 is less than Z5 is minus H4. So I can write P5 is equal to PATM plus rho A G H1 minus rho B G H2 plus rho C G H3 minus rho D G H4, or P5 gauge, which is P5 minus PATM, is equal to rho A G H1 minus rho B G H2 plus rho C G H3 minus rho D G H4. In a compressible fluid, the density is not constant. Because of that, we need to know how does the density varies with temperature and Z. For example, in atmosphere, we can assume that the air is a perfect gas. So we know that P is actually equal to rho RT. So if we substitute that in the equations, dP dz is equal to minus rho G, and rho is equal to P over RT. So we can write the equations dP dz is equal to minus Pg over RT. So in order to integrate these equations to find out how P varies with Z, we need to know how does, for example, the temperature varies with Z. So in atmosphere, we can divide the atmosphere into two parts. First of all, the first part is between 0 to about 15 kilometers. That region is called the troposphere, whereby the temperature varies linearly with Z. It's given by this equation, T equal to T naught, a reference temperature, minus alpha Z minus Z naught. So if we are to substitute expression for T in these equations and do the integration, we will get these expressions for pressure variation with Z. However, above 15 kilometers from the Earth's surface, we have reached a region which is called troposphere. So here, temperature is almost constant. So we can again substitute that into these equations to obtain how pressure varies with Z in stratosphere. So we have dP dz is equal to minus rho G. This is applicable to compressible and incompressible fluid. So if we assume atmospheric air as perfect gas, so we can write P is equal to rho RT. Hence, we will have dP by dz is equal to minus Pg over RT. Okay. So let us consider these two regions. First of all, the troposphere. So in troposphere, so we have T is equal to T naught minus alpha Z minus Z naught. So now we can substitute this into these equations. So we have dP by dz is equal to minus Pg over R. So now T is T naught minus alpha Z minus Z naught. So now if we consider, so let's say this is the Earth's surface, and this is a point naught, and this is another point called this point 1. So whereby the pressure here is P1, the pressure here is P naught. So this is Z naught, and this is Z1. We want to find out how does the pressure P1 in relation to pressure here. So if we integrate these equations, what we'll get, bring P here, 1 over P dP. So this is from P naught to P1, from naught to 1. And what we'll get on the right hand side is bring the constant out, minus T over R, and again integrate from Z0 to Z1. Then we have 1 over T0 minus alpha Z minus Z0 dz. Right. So if we integrate these equations, what do we get? We'll get log P from P0 to P1, and this must be equal to minus T over R. So if you want to integrate this, so first of all, log T0 minus alpha Z minus Z0. But if we differentiate this, we will have 1 over T0 minus alpha z minus z naught, but we have minus alpha here, so we have to divide by minus alpha here. So the whole thing is from z0 to z1. So this will give, so log p over p0 is equal to g over alpha r log t0 minus alpha z1 minus z0. So this will be p1 over t0, because z0 minus z0 is 0. So we'll have that. So we have log p1 over p0 is equal to log t0 minus alpha z1 minus z0 over t0. So bring this to this, so we have g over alpha r. So now we get the expression which is that remove this log, so we have p is equal to p0, t0 minus alpha z1 minus z0 over t0 to the power of g over alpha r. This is how pressure varies in troposphere. So now for stratosphere, we have T equal to Tc equal to T constant. So if I rewrite again, so dp dz is minus pg over rt. So if I substitute, then I have dp by dz is equal to minus pg over rtc, right? So if I integrate again, so I have 1 over p dp from again p0 to p that we want to find out must be equal to, so now everything is constant, minus g over r dc dz from z0 to z. So this gives me log p from p0 to p, and this is minus g over r dc z z0 to z. So I have log p over p0, and that is equal to minus g over r dc z minus z0. So this gives me p is equal to p0 e minus g over r dc z minus z0. So that's how pressure varies in stratosphere, in atmospheric air.